I am happy to announce the second speaker for today, Alexander Rolle, who is currently at TU Graz, and the title of his talk is Stable and Consistent Density-Based Clustering.
Okay, well, thank you for the introduction. It's great to be able to participate in this very interesting series of talks. So yeah, as the title says, I am going to be talking about a stable and consistent approach to density-based clustering, which is inspired by methods from TDA. This whole project is joint work with Luis Skokala. We recently posted a paper on the archive that contains all the results I'm going to talk about today. Okay, so I'll start by giving a quick outline of the talk. So I'll begin by recalling what density-based clustering is, or at least what I mean by that term, and also making a few general remarks about hierarchical clusterings and how we define them, and the notion of distance that we use between them. And then I will define a multi-parameter hierarchical clustering of any metric probability space, which we call the robust linkage. And this multi-parameter hierarchical clustering contains as one parameter slices several well-known approaches to density-based clustering. And so the idea of this project is that by choosing the right kind of one parameter slices of this multi-parameter hierarchical clustering, you get a one parameter hierarchical clustering algorithm that has nice properties and satisfies a stability theorem and is consistent. Okay. So yeah, I'll begin by talking a little bit about one way to set up density-based clustering. So if we let f be a probability density function on Euclidean space,
I don't think your slides are displaying correctly.
Okay, thank you for, oh yeah, I'm seeing a warning.
We still see your title slide. I don't know if that's by design.
Oh, you do? Oh, that is not by design, no.
We just see the title.
Let me try stopping the sharing and starting again. Let's see, can you see my slides now?
Yeah.
Okay, great. So you didn't miss much. All I showed you before was a outline of the talk. Although now with this setting, my computer isn't letting me advance the slides.
There might be a button at the bottom of the slide that you can press to advance it.
Oh, I see. Okay. All right. Well, let's see if this works. But you can still see my slides?
Yeah.
Okay, great. All right. Yeah, and thank you for telling me that something had gone wrong. So let's let f be a probability density function and let x be its support. There is a hierarchical clustering called denoted h of f of the support, where at the density threshold lambda, we let h of f at lambda be the set of connected components of the super level set of f at lambda. So this construction has been in the statistics literature for a long time. It goes back at least to the work of Hartigan in the 1970s. And it has appeared under many different names over the years. One of Hartigan's original names for it was the density contour tree. And so that's what I'll call it today. So the goal of density-based clustering is to approximate this density contour hierarchical clustering given a finite sample drawn from the density. And of course, one could state this problem in greater generality. For example, one could consider a density function defined on some lower dimensional manifold, but for now, we'll just keep things simple. And so in this context, people use the word consistency to mean roughly the following. We say that a hierarchical clustering algorithm A is consistent if given a sequence of IID samples drawn from the density, the hierarchical clustering we compute of the samples converges in probability to the density contour hierarchical clustering. And so this is not a precise statement. I have not said what it means for a sequence of hierarchical clusterings to converge. There are various ways to make this precise, and I'll talk about one way to do that in a minute. So now the goal of this project is to define a consistent hierarchical clustering algorithm with good stability properties. And what I mean by that is I want my hierarchical clustering algorithm to satisfy a stability theorem that is deterministic and that does not depend on the input being a sample from some particular kind of distribution. So these assumptions are, this whole setting of density-based clustering is a nice way to set up the clustering problem, but I want my stability theorem to hold even outside of this setting. Okay, so I've been using the word hierarchical clustering, and I'll quickly say what I mean by that. So here's the first definition. If X is a set, a clustering of X is just a set of non-empty disjoint subsets. So in particular, I don't require it to be a partition. There is a poset of these clusterings. So the set of all clusterings is partially ordered by the refinement relation. So we say C is less than or equal to D if for each cluster A and C, there is a cluster B and D with A contained in B. And now with this poset of clusterings in hand, we can say that a hierarchical clustering is simply a map of posets into this poset of clusterings. And I'm gonna require the domain of this map to be a finite product of copies of the positive real numbers with the usual ordering, or the positive real numbers with the opposite ordering. And so this is obviously not the most general form of indexing posets one could consider, but it'll be enough for what I'm talking about.
So by capital I think of sort of the parameters or the height that you're using in your.
Yeah, exactly. And so this is, so the first example here is the density contour hierarchical clustering that I mentioned on the previous slide. And so this is a one parameter hierarchical clustering that is contravariant. So it's a map of posets where the domain is just one copy of the positive reals with the opposite order. And then another example, this robust linkage that I said I would talk about, this is going to be a 3-parameter hierarchical clustering where that is covariant in the first 2 parameters and contravariant in the third. So this definition that I'm talking about of hierarchical clustering, on the one hand, it's quite general in that I require a hierarchical clustering to be just any map of posets of this form. I don't ask for any tameness conditions or any other structure. But actually this, the kinds of domains that I allow for this map is actually the minimum level of generality that I need, because I want to be able to talk about multi-parameter hierarchical clusterings, and I also want to let them be covariant in some parameters and contravariant in others. Okay, so now that we've talked about that, so this definition is just the same definition from the previous slide, I can tell you the notion of distance that we use between hierarchical clusterings. So if I take 2 hierarchical clusterings of the same set, then there's automatically an interleaving distance between them. And if I fix a correspondence R between 2 different sets X and Y, and H is a hierarchical clustering of X, and E is a hierarchical clustering of Y, then there is a natural notion of interleaving between H and E with respect to R. So by optimizing over all correspondences, we get a distance, which we call the correspondence interleaving distance, between hierarchical clusterings of different sets, but of the same type, with the same number of parameters and the same covariance and contravariance. So this correspondence interleaving distance is not new. It generalizes a distance of Carlson and Memley that was defined for certain 1 and 2 parameter hierarchical clusterings with some tameness conditions. So the main observation here is just that if one is willing to work in this setting where a hierarchical clustering is simply a map of posets of this form, then one can set up this correspondence interleaving distance in a clean way. And this is the distance that we'll use to state both our stability and consistency results. So I said that the notion of consistency I was talking about before was not precise because I hadn't said what convergence of hierarchical clusterings is. But once you have a metric on hierarchical clusterings, then it's easy to make that notion precise. One can just ask for convergence in probability in the metric, and that's what we'll do. Okay, so now I can define this construction robust linkage. So let X be a metric probability space. I first define a bifiltration of X, where at the position Sk, I take those points in X where this integral, which is sort of like a kernel density estimate using the kernel capital K and the bandwidth S, is greater than or equal to the density parameter lowercase k. And then I can form robust linkage. Like I said, it'll be a 3-parameter hierarchical clustering by first taking this bifiltration of the input and then using the 3rd parameter as the parameter for the single linkage clustering. So I should say a little bit about connections to things in the literature. So if one uses the uniform kernel and then and sets S equal to T to get a 2-parameter thing, and then if instead of using single linkage you apply Viator's RIPS, you get what's been called the degree RIPS bifiltration, which has been studied by various people, including Lesnick and Wright and Blumberg and probably others. And so the generalization here is just that we're allowing for other choices of kernel as well as the uniform kernel. And then I said that this would contain some well-known approaches to density-based clusterings. So I'll talk about that now. So again, if K is the uniform kernel and we fix the density parameter lowercase k, and we set T to be some constant multiple of S, then one obtains the robust single linkage algorithm of Chowdhury and Dasgupta. So this is a popular hierarchical clustering algorithm, and as far as I know, it was one of the first that people proved a consistency result for, and it was Chowdhury and Dasgupta who proved the consistency of robust single linkage. So this is sort of a horizontal slice of the robust linkage where the density parameter is fixed. If sort of orthogonally we fix the spatial parameters S and T, one obtains the filtration of the RIPS graph of X with respect to the parameter T by the kernel density estimate, or rather a constant multiple of the kernel density estimate given by the kernel capital K and bandwidth S. And then one gets a hierarchical clustering by taking the connected components of this filtered graph. And this is a popular way to produce the input to the tomato clustering algorithm, which is one of the most well-known TDA-inspired approaches to density-based clustering. Okay, so now I can talk about our first result, which is a stability theorem for this robust linkage construction. So robust linkage is uniformly continuous with respect to the Gromov-Hausdorff-Prokhorov distance on compact metric probability spaces and the correspondence interleaving distance on 3-parameter hierarchical clusterings. And if you define robust linkage using the uniform kernel, then it's 2 Lipschitz. So I'll just remark here that it's possible to prove this theorem by first proving a stability result that is sort of analogous to this just for the bifiltration that I defined on the previous slide before applying single linkage. And so that makes it easy to prove stability results for other constructions based on this bifiltration. For example, the construction you get by applying Viator's rips instead of single linkage. Now, let's let gamma be a curve in the robust linkage parameter space. So it's a parameterized curve in 3 space that also respects this poset structure that we have when we think of 3 space as the robust linkage parameter space. And then if I take a curve gamma like this, I can restrict robust linkage along this curve and get a 1 parameter hierarchical clustering, and this is what we call gamma linkage. And so then as an easy corollary of our stability theorem for robust linkage, we get a stability theorem for gamma linkage. So if gamma is continuously differentiable and its derivatives are bounded away from 0, then gamma linkage is uniformly continuous with respect to these same metrics. And again, if robust linkage is defined with the uniform kernel, then gamma linkage is Lipschitz with a Lipschitz constant that depends just on the derivatives of gamma. And so this is sort of well-known behavior that if you use slices like these ones in which all of the parameters vary, then these slices inherit stability properties from the multi-parameter object that you're slicing. But I should emphasize that these assumptions are really necessary. So on the previous slide, we saw that robust linkage includes some popular approaches to density-based clustering by taking 1 parameter slices. And those were 1 parameter slices where you fix some of the parameters. And it's easy to see by example that those methods are not stable with respect to Gromov-Hausdorff-Prokhorov small perturbations of the input. So if you want to get this kind of stability, you really do need to restrict to slices that in which all of the parameters are allowed to vary. Okay.
And that's where the derivative is bounded away from 0.
Yeah, exactly. Exactly. Yeah. But that's all you need. So it's an interesting, I mean, in practice, of course, one expects to use sort of simple slices, but at least for the point of stability, all you really need is this condition on the derivatives. Yeah, okay, so the last theorem I'm going to talk about is a consistency theorem for this gamma linkage. So if f is a continuous and compactly supported probability density function, and x sub n is a sequence of IID samples, and I let gamma theta be an admissible family of curves, and I'll say in a minute something about what that means. Then for every n, there is a parameter theta such that the correspondence interleaving distance between gamma theta bar linkage of x, and I'll say something about what gamma bar is again in a minute. This correspondence interleaving distance between the gamma bar linkage of the sample and the density contour hierarchical clustering goes to 0 in probability. And so this is the sense in which we prove consistency for gamma linkage. So what is an admissible family? Roughly speaking, an admissible family of curves is just one that's big enough and that covers the parameter space in a sort of sufficient way. So to prove this consistency theorem, you do not need to consider all possible choices of parameter. You don't need to consider all possible curves in the robust linkage parameter space. And so, for example, you could restrict to the curves that are defined by linear functions, and that forms an admissible family. And this gamma bar is a reparameterization of gamma that depends only on gamma and the ambient dimension. And this is pretty standard in these kinds of consistency results, that one has to be willing to reparameterize in a way that takes into account the ambient dimension. And so the last thing I'll say about this theorem is just to emphasize this theorem uses the same kinds of curves that I was talking about on the previous slide, these curves in which all of the parameters are allowed to vary. And we have to use those those kinds of curves for this theorem because we used the stability theorem from the previous slide in the proof. Okay, and so I'll just finish with a couple quick final remarks. So in this paper that we put on the archive, we also talk about flattening. In practice, a common reason that people construct hierarchical clusterings is to then extract a flat clustering from the hierarchy. And very roughly speaking, the idea is often that one wants to extract flat clusters that persist for a significant period of time in the hierarchy. And we studied a couple of well-known procedures to do this and show that they have stability results that can be combined with our stability result for gamma linkage. So they can be stated using the same metrics that we use on hierarchical clusterings. And this is one of the main motivations for studying the stability properties of hierarchical clustering algorithms. And then the last thing I'll say is just one point of future work. It would certainly be interesting to consider weaker hypotheses on the density function. For example, letting it be supported on a lower dimensional manifold in the consistency result. And we hope that the ideas that we've been using for this consistency result should also work in greater generality. Okay, I'll stop there.
Okay, thank you. Questions? Yeah, so remember you have to unmute yourself, or you can also just type your question into the chat window.
Alex, I had a question about flattening. So can you describe a little bit again from a high level what flattening is? Is it where I take a hierarchical clustering technique, like producing a dendrogram, and instead try to find a particular slice, which I call my clusters? Not
right. So I guess that probably is the prototypical flattening process, but that is not the process that we consider in our paper. So there are a couple of procedures which have been considered in as part of sort of well-known flat clustering algorithms. So for example, the tomato clustering algorithm begins by constructing a hierarchical clustering, and then rather than extracting a flat clustering by just choosing some index, it prunes the flat clustering in some careful way, and then it takes clusters from the hierarchy that persist for sort of a significant amount of time in the hierarchy.
I see. So you're choosing just a single partition, but yeah, that single partition is sort of informed by multiple scales in your hierarchical.
Exactly. That's the idea. And
cool.
And again, the idea is that this allows you get what in many applications you actually want, which is a single clustering of your data set, but you still do this sort of persistent space approach where you're considering your data set at multiple scales.
Cool.
And both of the approaches that we talked about, the one underlying the tomato algorithm and another that is part of something called the HDB scan clustering algorithm, both of these processes make sense for arbitrary hierarchical clusterings, basically. So in particular, they could be applied after this gamma linkage hierarchical clustering algorithm that I've been talking about. And
then one of the stories that you found out is that you sort of need to look at multiple scales to get something that's stable.
Right, exactly. Yeah. So a lot of these hierarchical clustering algorithms that are supposed to take into account noise, of course, they track multiple scales because they're hierarchical, but often the part of the in order to get just a single one parameter hierarchical clustering, some other parameters are fixed.
Mm-hmm.
And so yeah, the whole idea of this approach is that by letting all the parameters you're considering vary, you get something with better stability properties.
Cool, I like that a lot.
More questions for the speaker?
Yeah, maybe me.
Yeah.
Could you please go back to the slide 8? to
Oh,
aid
sure.
to the theorem? Okay, so so this this parameter theta,
Yes.
for every n there is a parameter. So the thing is that I don't understand this limit, right? So this theta changes with n and could go to infinity, right?
Oh, right. Well, so this parameter is really just a choice of, I haven't said what capital theta is, and that's part of.
Yeah, it's a choice of this flattening, right? It's
a choice. It's a choice of the curve. So, for example, if your admissible family of curves was all of the curves defined by linear functions, then this theta would be something like R2. It would be the two coefficients in the linear function that defines the curve. And so what this says, and this is another way, by the way, in which I have sort of not been very precise about what consistency means. And this is often sort of a subtle point in consistency results. So the idea is that we hope that as our samples get bigger and bigger, the hierarchical clustering we compute of the sample should approach the density contour hierarchical clustering, this H of F. But of course, hierarchical clustering algorithms take parameters, and we don't expect that we get this convergence with respect to any arbitrary choice of parameters. And so usually these consistency results are saying instead that there should be a strategy for choosing parameters. And so this should take the form of telling you for every n, for every sample size, I choose a parameter. So then as I look at bigger and bigger samples, I change my parameters to be sort of appropriate with the size of my sample. And then in this way, I get a sequence of hierarchical clusterings. So both changing the sample and changing the parameter. And then this sequence.
Do you know how it converges? For example, is it monotone convergence? Like I would like to, to say that this doesn't happen that like, you have to go really far.
Right. So this is, so establishing the rates of convergence is still future work. I mean, I can say that if your sequence of samples is monotonically improving in the extent to which it's approximating F. So if it's monotonically improving in the Gromov-Hausdorff-Prokhorov distance, then yes, this the correspondence interleaving distance between the two hierarchical clusterings will also be monotone.
Okay, thank you. So I would like to ask everyone to unmute yourselves and so that we can thank Alexander again. Thank you for joining us, and you will see us again on Wednesday if you attend one of the standard applied topology network talks, or next Monday for the continuation of the ATMCS online session.